Let's add a few more points about short duration extremes from a workshop summary report and a science paper that came out of that meeting. This is from the UK group led by Haley Fowler. So here is a nice summation of project's key questions, a project called Intense, which was under GUX, which focused on extremes, short duration extremes, SC here. I don't remember the acronym, but you can look it up. At the center here is how can we use information from climate models better to inform adaptation. So this is about climate change adaptation and the specific goals of dealing with extreme rainfall, short-term extremes. How has sub-daily extreme precipitation changed? As we saw in the tropics, for example, there is not even the required amount of finely resolved data both in space and time. Over UK there is more data, and there is a global synthesized data set of sub-daily rainfalls as well, but nonetheless more specific studies tend to be regional, like over Europe, and question of course is whether they can then be extrapolated to global other regions as well. How are extremes related to temperature and moisture? So we looked at that precipitation theory we did in terms of precipitation efficiency, vertical motion, and the DQD what was it? DQDP, DQSDP term. How do large-scale features of the atmosphere and oceans influence the extremes? So here we are talking about fast and slow scales that we talked about before, where land and atmosphere can respond quickly to radiation perturbations and warming, whereas the ocean is slower to respond, but it is the massive moisture source for precipitation over land. For example, we said extremes over India, the widespread extremes over India seem to get a lot of their moisture from the Arabian Sea, which is warming very fast. So when you go to continents that are much bigger, like Europe, Eurasia, or the US, then what is the ocean's role near the coast versus the interior? What are the orographic features that matter for the extremes based on the direction of flow? For example, over India, southwesterlies are coming over the Western Ghats, and over the US, westerlies are coming over the Rockies. And you also have differences between snowfall extremes and precipitation extremes, which I'm not going to get into, but Paulo Gorman's paper does talk about it. Okay. Finally, thinking about anthropogenic emissions, how will extremes likely respond to future warming? That's always the key question, right? We are trying to deal with what's happening right now, like the widespread extremes, short duration extremes, extreme floods. This July 2021 was a humongous shock to lots of places, starting from massive floods in the US, in Europe, in China, in India, and so on. So extremes are already here. This is from the same report, looking at what is needed as we go forward. So here we are looking at knowledge path on relationship between precipitation extremes and global warming, consensus and missing pieces. Additional studies are required to dissipate uncertainties linked to the influence of large-scale circulation dynamics, latent heat release, and moistatic stability, changes in storm characteristics, and temperature stratification. So you're talking about stability, how the storms themselves change, how the moistatic stability is being affected by global warming, and of course large-scale circulation and condensation heating as we load up the atmosphere with more moisture with the warming. International collaboration is needed to increase model confidence, to evaluate uncertainties, and to advance scientific knowledge on poorly understood phenomena like cold pools, wind shear, and precipitation efficiency, which of course is a key unknown variable as well. So here we are, international collaboration for model configuration, confidence, and uncertainties evaluation. The knowledge path and missing pieces are represented here with the convective process modeling, convective permitting models crucial to represent climate change, Clausius-Clapeyron rates, long duration, heavy precipitation scales with temperature at Clausius-Clapeyron rate, so it's approximately 7% per Kelvin. Hourly extreme precipitation can exceed Clausius-Clapeyron scaling, as we said. And missing pieces include influence of changes in large-scale circulation dynamics, which is not fully understood yet, changes in moist static stability, which is not fully understood yet, influence of latent heat release in terms of its impact on the fast scales, slow scales, short duration extremes, and just local feedbacks that can give you this super Clausius-Clapeyron scaling. Changes in storm characteristics, temperature stratification in winter for snowfall extremes that I mentioned, precipitation efficiency, entrainment, detrainment. So these are convective processes that are not completely understood and are being parameterized and show some improvements in processes when they are included, like dilute plume approximation and convective momentum transport and so on, cold pools and wind shear effects. Okay. So anthropogenic intensification of short duration rainfall extremes also came out of this UK project, INTENSE project, again led by Haley Fowler. Let's just look at a few key points. Heavy rainfall extremes are intensifying with warming at a rate generally consistent with the increase in atmospheric moisture, which is Clausius-Clapeyron scaling, for accumulation periods from hours to days. So there is a threshold above which the Clausius-Clapeyron is a good estimate of scaling for rainfall extremes. In some regions, high-resolution modeling observed trends and observed temperature dependencies indicate stronger increases in short-duration, sub-daily extreme rainfall intensities, up to twice what would be expected from atmospheric moisture increase alone. So they are at 15% or above, in some cases even 30%, but it's unclear if those are very specific cases or they are global phenomenon. Stronger local increases in short duration extreme rainfall intensities are related to convective cloud feedbacks, but the relevance to climate change is uncertain owing to modulation by changes to temperature stratification and large-scale atmospheric circulation. So we are changing stability, which can inhibit rainfall and extreme rainfall, and large-scale atmospheric circulation, which can reduce vertical motion and inhibit these kind of convective cloud feedbacks which are observed in the current climate. It's unclear whether storm size will increase or decrease with warming. However, increases in rainfall intensity and spatial footprint of a storm can compound to substantially increase the total rainfall during an event. So you have to look at intensity, duration, and frequency. Okay. Evidence is emerging that sub-daily rainfall intensification is related to an intensification of flash flooding, at least locally. This relates to how to plan for adaptation as well as considering how local these are. Future projections have to be able to say something about local impacts with some confidence for adaptation to be possible. This intensification will have serious implications for flash flooding globally and requires urgent climate change adaptation measures. Obviously, we don't have infinite resources, so you cannot simply find ways to adapt everywhere. So more local and region specific are the projections of short duration extreme events. the more likely there are going to be better adaptations and fewer maladaptations. If you put a lot of funds into adapting in a place where short duration extremes may actually decrease, okay, some examples have been found over Europe where short duration extremes have decreased in the historic period. So this has to be understood very well, but more especially for projections into the future, because the models in general dominate the uncertainty in the projections for shorter duration, like the next decade or two. But when you go into longer periods, longer term projections out to 2060 to 2100, it's the scenario uncertainties that begin to dominate projections. So how do short duration extremes and in general precipitation extremes get affected by model uncertainties versus scenario uncertainties versus just the representation uncertainties of processes like convection, convective feedbacks versus just process uncertainties in knowing how things like precipitation efficiency, large-scale circulation, condensation heating, stability of the atmosphere, etc. will respond to warming. These are really challenging issues, but that's why we are trying to better understand them and trying to improve the models and observations as well to reduce uncertainties, improve process understanding, improve predictive understanding, and also improve projections and reduce uncertainties in projections, improve the scales of the projections, spatial scales and temporal scales. Okay.